Thank you. I would like to thank Chiara and Marcelo for working very hard to get this workshop going, and also for managing to get people in that room. I envy you. I hope that soon we all will be able to travel. So enjoy the gathering. It's just wonderful to see you there. Okay. So I will talk about interactions, systems of particles that are interacting, where it's relevant to look at beyond binary interactions. And let me give outline of the talk. So first I will talk due to nature of the topic of this workshop. So first I will review some work from some time ago on quantum systems. And this is joint work with my colleague Thomas Chan. And we are going to be discussing going from bosons to nonlinear Schrödinger equation. And specifically, I will mention how when we looked at ternary interactions that led to quintic nonlinear Schrödinger. Then we will look at the classical systems of particles. This is joint work with Joachim Ampatsoglu, who was my PhD student and is now postdoc at Courant Institute. So we want to generalize Boltzmann equation. So we derived something that we call ternary Boltzmann equation. And also I want to tell you about something that we are very excited about. That's relatively recent work on binary ternary Boltzmann equation. So let's see, my computer is complaining that it's overheating. So we will see what happens. Okay, let's start. So let's look at the quantum system first. So as we know, at very low temperatures, both gases are characterized by macroscopic occupancy of a single one-particle state, which is known as Bose-Einstein condensation. So although it was predicted quite some, basically 1920s. So in 1920s by Bose and Einstein, it took quite some time to get first experiments. And the experimental realization came in 95. There was a team at University of Colorado, Boulder led by Kernel and Boltzmann, and they worked with the rubidium atoms. Then there was a team at MIT led by Ketterle, and they worked with sodium atoms. So they started, also there was a work at Rice, since I'm from Texas, I want to mention Texans also. So from Rice, Houellebecq worked on lithium, but the difference with Houellebecq's work and his team is that their experiments were not originally stable. So then they needed to figure out how to make them stable. So by the way, these experiments were very relevant in physics, and they started the subfield of physics that are related to ultra cold atoms. So it was very hard to actually achieve 0 Kelvin and temperature near 0 Kelvin, and it was a part of the problem of how to do it physically. So subsequently, Kernel, Boltzmann, and Ketterle received the Nobel Prize for physics in 2001. Of course, mathematicians have been looking at this question too. And first they looked at the static problem in time. So around 2000, problem was formulated and solved in certain situations by Lieb, Siringer, and also Lieb, Siringer, Yingwanson, and Lieb, Yingwanson, and their friends and collaborators. But I want to mention this is still quite active topic, even in static case. And there are recent results by Nam, Rougerie, Siringer, by Boccato, Bernanke, Senatiempo, and Schlein, and some other teams. I didn't exhaust the list. But what I'm trying to say, even static problem in time is still hard, and people are working on that. In terms of experiments, so the situation is that you look at the atomic gases and you put them into magnetic forces, you trap them using magnetic forces, and you cool them at very low temperatures. So then you turn off magnetic traps and you observe that all these particles behave like one. So here is a picture of velocity distribution data for rubidium atoms, before, just after, and sometime after the condensation. So there is this picture that appeared at the cover of the Science magazine at the time of the experiments, which also tells the story in a artist way. So mathematically, how can one formulate that? And actually, beauty of the quantum picture is that there are various ways of getting the results nowadays. But one way of thinking about that, you have n particles and bosons, and with a certain, you have an absolute value of the wave function is probability density that particle I is at the position xi. So you have, let's say, n of them, and you want to understand that system. So what you can do, you can look at the energy, ground state energy for this system, and it tells you about ground state energy for the n particle system. You divide that by number of particles, and you wonder what happens as n goes to infinity. So you have, as auxiliary step, you have this situation of infinitely many particles. So it turns out when you average in this way, what you get is ground state energy of one particle that evolves according to nonlinear Schrödinger equation. So that's connection between systems of bosons and nonlinear Schrödinger. Okay, so more precisely, you look at the n particle system evolving according to n-body linear Schrödinger. So I partial with respect to t of the wave function, you have a Hamiltonian acting on the wave function. I will show Hamiltonian because I will talk about ternary interactions. I will show relevant Hamiltonian for ternary interactions. For now, think there is a kinetic part, and then there is a potential, which is typically two-body potential. So since Hamiltonian is self-adjoint, and we are talking about linear system of n equations, this is globally well posed. Okay. However, the fact that it's globally well posed is pretty useless when you look at the relevant number of particles, even for dilute Bose gas, that's like 1000, or if you look at the stars, that's like 10 to the 23, 10 to the 30, and so on. So numerics or our form or people's formula that you can write is useless. So fortunately, what's happening is that physicists care about average behavior, typical behavior of a particle. So one simplification comes from looking at the average, and the other simplification comes from looking at the limit as number of particles goes to infinity, hoping that what you observe in the limit will help you figure out what's happening for finite but large n. Okay. So in the quantum part of the story, there are many ways now of doing that. I will not be able to mention everybody, and not everybody working on this is on this slide. I just want to mention some ways of thinking about this. So the first rigorous works, when you look at time evolution also, were done in 70s and 80s. And there were two approaches at the time. One, HEP was actually the first one, observed connections between n-body particle systems and nonlinear Hartree equation. And he did that for smooth potentials in the Hamiltonian. And then Ginevra and Weil were able to generalize their work, HEP's work, for more singular potentials. However, this was done using quantum field theory. The first convergence results from n-particle systems to nonlinear Hartree equations were obtained by Spohn for bounded potentials. So this is at least two approaches that were present in 70s and 80s. All this was revived in last 10 to 15 years. So quantum field theory approach was revived and became very sophisticated. Many people working on that, Rodnyansky, Schlein, and Grilakis, Macedon, Margetis, and Shu and Chan, and various subsets of this group. Then I just want to mention also the work of Peter Pickel, which is different. He has a very nice way of characterizing what condensation means, and still quantum field theory approach, but different than for example, Rodnyansky, Schlein, and Macedon, Margetis. So then math physics approach that was started by Spohn was generalized to allow singular potentials. And most important work along these lines is by Erdős, Schlein, and Yao, and I will tell us a little bit about that work. So that work inspired PDE people to jump on board in some sense, and thanks to Kleinerman and Macedon, because they reformulated part of the problem in a language that was close to PDE people. So that nowadays there are many people who work in dispersive PDEs who are also studying connections between dispersive properties and many-body systems. So I wrote here some of us. Okay. So the topic of this talk is ternary and beyond binary interaction. So let me get into that. So quite some time ago, around 2009, with Thomas Chan, we wondered what happens with the quantum system of particles that allow higher order interactions. So you might wonder, why did we ask that question? So until then, people looked at pair interactions. However, even when you look at nowadays information on Wikipedia, it will tell us that it's relevant to go beyond binary for the quantum system. So once the interaction of the Bose gases with the background field of matter is included, for example, phonons or photons, averaging over the background will produce actually linear combination of effective little n particle interactions, quadratic, cubic, and so on. Not only that you would have just ternary interactions, but you would have binary, ternary, and so on, and the linear combination of those. On the other hand, math inspiration came to us from the works of people that studied quintic nonlinear Schrodinger. The reason is because 3 particle interactions in this picture lead to quintic NLS. And as we know, quintic NLS is energy critical in 3D. There were many works. I'm mentioning here Colliander, Kiel, Stafilani, Takao, Katao, global level posedness for the defocusing problem in 2008, and also mass critical problem in 1D that was solved relatively recently by Benjamin Dodson in 2016. What I'm trying to illustrate here is that quintic NLS has attracted a lot of attention in the dispersive community. Okay, so now how did we derive quintic NLS at the time with Thomas? So the starting point is linear Schrodinger equation, n-body Schrodinger, and we model 3 particle interactions using this Hamiltonian here. So Hamiltonian, so we have there is a kinetic part on the Hilbert space of L2 symmetric functions in RDN. So we are talking about n particles, and each of them is in RD. Okay, so therefore RDN, and L2 symmetric because wave functions are fully symmetric with respect to permutations of arguments xj, because we are talking about bosons. So there is a kinetic energy here, j going from 1 to n minus Laplacian with respect to xj, and then there is a potential 3 particle potential. So it's rescaled here such that in the weak limit it goes to delta function, so that we get nonlinear Schrodinger with the power nonlinearity as opposed to Hart-3 equation with the convolution. So we have potential here that describes how I and j and I and k interact. And then you sum over all ijk, and then you balance the fact this is triple sum, this is single sum, you want to use energy eventually, so you need to balance this. This is happening in so-called Gross-Pitaevsky scaling. So with this Hamiltonian, so what did we do at the time? I'm giving just a very global picture because I want to talk about classical system of particles for this talk. So the first step is you have n-body Schrodinger equation. You look at the limit as number of particles goes to infinity. And what you get is here denoted by GP, that stands for the Gross-Pitaevsky hierarchy, which is this infinite linear hierarchy of equations. And so that's the first step, convergence. Then you can say, okay, so what do you do once you have this infinite hierarchy of equations? The point is this Gross-Pitaevsky hierarchy admits a special solution which is factorized if factor solves nonlinear Schrodinger. Okay, so then that's derivation of nonlinear Schrodinger, because if you prove uniqueness of the solutions to this auxiliary Gross-Pitaevsky hierarchy, then you have derivation of NLS, because then if you start with factorized data for the Gross-Pitaevsky hierarchy, you will know that solution will stay factorized and therefore you get NLS. So actually uniqueness is quite hard in the case of the Schrodinger, and this was done, so I'll tell you a little bit in the seminal work of Erdős, Yao. Now there are there's more than one way to do uniqueness. So Erdős, and Yao in the papers around 2006 and 2007 accomplished uniqueness using highly sophisticated Feynman graphs. Of course, this was based on oscillatory properties of certain integrals. So although there are Strickhart's estimate there, although not maybe explicitly said that they're using their oscillatory properties of integrals, so there are Strickhart's estimates happening there. Kleinerman and Macedon, motivated by the work of Erdős, and Yao, reformulated uniqueness part, but it was in a different space, and that's very important. And actually their result was in a different space, and it was conditional. So what they did is you have these nasty Duhamel formulas, and they converted them to with a basically more, they make analogy between such nasty Duhamel formulas and certain matrices. And then they introduced the board game argument that helps them introduce notion of equivalence. So the point is you can easily count classes of equivalence. This is relatively simple combinatorics. And the point of their work is for each class of equivalence, you use space-time estimates. And they obtain by using a Fourier transform in space and time and obtaining estimates a la Strickhart's, really. However, the result was conditional. So Stafilani, Kirkpatrick, and Schlein were the first to be able to use their result in 2D to get derivation of NLS. with Thomas Chan, Christian Hansel, and Robert Ziringer, we got a different proof of uniqueness, although we were not after that. We wanted to understand long-time behavior, and somehow along the way, we realized that there is another way of proving uniqueness, unconditional uniqueness. And for that, we used this quantum definite theorem that was at the time rephrased by Lavin, Nam, and Rougerie. And one can think about it as a representation theorem for solutions of the infinite hierarchies. So that's another way to prove uniqueness in 3D. Now, going back to ternary problem, with Thomas in 1D and 2D, we used the Kleinerman-Macedon approach to prove uniqueness and got clintic nonlinear Schrodinger. In 3D, Hong, Taliaferro, and Shi implemented the quantum definite approach and got uniqueness. I also want to point out that Jikui Shi, who was my student at the time, got a linear, was able to derive a linear combination of power nonlinearities. So generalization to Schrodinger, which is really relevant from the physics point of view that we said at the beginning. So I think this is all that I was planning to say about derivation of the quintic and higher order nonlinear Schrodinger. I want us to remember that the way how we approached this problem was by changing Hamiltonian and by modeling higher order interactions via potential. So now I want to switch the story to classical particles. Okay. So we will work with Boltzmann equation. So we'll just quickly review Boltzmann. I think, unfortunately, I had a meeting, so I missed Sergio Simonelli's talk yesterday. I believe that he talked about related things. So I will just quickly review some things here. So we know, as Lorraine mentioned a few minutes ago, Boltzmann equation has been studied since 1860s and 1870s when it was introduced by Boltzmann and Maxwell. So here we have the equation that models the dynamics of a dilute gas. So it's for the position x, the time t, the x is in Rd, positive time, and velocity v in Rd. So it describes evolution of the density of F at x, t, and v of gas particles. On the left-hand side is material derivative of F, so it's how it's transported. And on the right-hand side is Q2 operator, which is a quadratic integral operator that describes the change of F due to instantaneous binary collisions of particles. Now, the form of Q2 depends on the type of interactions between particles. So let me just draw some pictures here, just for the language. So for a pair of particles, let us denote by V prime and V1 prime their pre-collisional velocities. So then one can form a relative pre-collisional vector and also unit vector sigma in that direction. So let us denote by V and V1 their post-collisional velocities. So then we can talk about relative post-collisional vector and unit vector, in this case denoted by U hat. This hat has nothing to do with the Fourier transform. So unit vector in that direction. So then if you assume that you have elastic interactions, so you have a conservation of momentum, which is the first equation, and you have a conservation of energy. So having conservation of momentum and conservation of energy, you can express post-collisional velocity, you can express here pre-collisional velocities in terms of post-collisional velocities and sigma. So keeping in mind that you can express pre-collisional velocities in that way, now we are ready to write a formula for Q2. So for the collisional operator, Q2 is defined as, so here we didn't use the notation, F is the density at x dv. So if there is a prime, that means it's at v prime. If there is a prime and 1, that means it's in velocity v1 prime, and so on. So what you have here is this difference between gain and loss term of f prime 1 minus f1, and then you have a kernel that I will tell us about. But the point is that you got rid of pre-collisional velocities v1 prime and v prime. So now you're left with v and v1. You integrate v1, and so you integrate first sigma on the sphere as d minus 1, and you integrate v1, so you're left with something that's evaluated at x, t, and v. Of course, this little b is very important, the kernel, and this was mentioned by Lauren a few minutes ago. So typically one assumes that little b has the following format, that it's absolute value of this relative precollisional vector u to a power a, and then dependence on the cosine of the angle. If you remember the picture, this is the angle that we are talking about, angle between relative precollisional and relative postcollisional velocity. Okay. So the case as the same convention as Lauren used when a is between, so actually let me read this from 3 to 1. When a is between 0 and 1, this corresponds to variable hard potential case. Actually a is equal to 1, it's hard sphere. A0 is Maxwell molecule, and this is a case where there are certain Fourier transform techniques that allow results that one can obtain specifically in that case. And then when a is between -d and 0, that's soft potential case. Okay, so that's all that I wanted to say about Boltzmann itself. I want to talk about modeling equation that's generalization of a Boltzmann in some sense, or a toy model toward generalization. So Boltzmann equation takes into account only binary collisions of particles. Ternary or higher order collisions are neglected due to lower probability of occurring compared to binary. So one actually sees this in derivation of the Boltzmann equation, because one considers all these higher order interactions, and you show that in a scaling, that's Boltzmann-Grad scaling, these guys go to 0. Okay. However, when the gas is dense enough, higher order interactions are much more likely to happen. So let me give an example for this. So example for such a situation is colloids. So this is a non-crystalline substance that consists either of large molecules or, for example, of ultramicroscopic particles of one substance that are dispersed through a second substance. Think foam or milk, okay? So if one looks at the colloid situation, then there are papers, physics papers. One of them is by Roos and von Gunberg, where they claim that multi-interactions among particles are relevant, and they are actually relevant, and they contribute to the grand potential of a colloidal gas. And they say that they model that this is modeled by a sum of higher order interaction terms. So this is not to say that we are modeling colloids. This is just inspiration that we have that's related to what we do. So with Joachim and Patsogu, what we want to do is we want to introduce and rigorously derive from a system of classical particles the kinetic model that goes beyond binary interactions. So, and we want to introduce, it goes beyond binary by incorporating a sum of higher order interaction term in the Boltzmann equation. So we would like to derive an equation that looks like 2.4. And we hope that it could serve as a toy model for non-ideal gas. So here is the equation. So on the left-hand side, it's transport of the density, still the same as for Boltzmann. So delta Tf plus V dot gradient xf. On the right-hand side is a finite sum, k going from 2 to m of qk's. Qk is the kth order collisional operator. Specifically, when k is 2, we are talking about Boltzmann. It's just Q2. And its sum goes from 2 to m. M is the accuracy of the approximation. Okay, so only after we played with this a little bit with Joachim and we derived, I will tell you about that actually. The first we derived it in the case when it was just Q3 case, when case 3. Only after we did that, we realized by talking to Irene Gamba, our colleague, that Irene, together with Bobilov and Cercigliani, proposed the model like 2.4 in the case of Maxwell molecules. And they have 2 or 3 papers, a sequence of papers where they study this model for Maxwell molecules. They didn't derive it rigorously, but rather they studied well-posedness and properties of moments for this model, okay? So what we want to do, we want to derive this equation. So I want to point out that when m is equal to 2, if we go back, m2, so that's just the case, k is equal to 2, so that's regular Boltzmann equation. Deriving Boltzmann from classical many-particle systems is itself a challenging problem. So for hard sphere interactions, it was pioneered by Lanford in 1975, and this work was relatively recently revisited by Gallagher, Sandermon, and Texier. This is hard sphere case. For short-range potentials, the analysis has been done by a student of Lanford at the time, King, and then revisited by Gallagher, Sandermont, Texier, and then many other colleagues have studied this. I'm mentioning here, for example, the work of Pavlović, Safirio, and Simonella from 2014. These works that I'm mentioning are using so-called BBGKY hierarchy and marginals. This is related to what we do. Nowadays, people are exploring other ways of doing this. The reason why I'm saying that there are still questions related to that, because some of these problems are done locally in time, unless one looks at the linearized equation or has some other assumptions. Okay. So the case n is equal to 3, so that's binary ternary Boltzmann equation, because that means that we would have Q2 and Q3, some of them. So this, to the best of our knowledge, has not been studied. So in addition to understanding binary interactions and ternary interactions, this would require understanding their mutual interactions. So we did that with Joachim recently, but I will tell you a little bit, I will tell you about that towards the end of the talk. I first want to talk about just Q3 case, and then I will look at both. Okay, so what I will focus on right now is derivation of the ternary Boltzmann equation. So we are guided by works of Lanford and Gallagher, Sandermont, Texier in terms of derivation of the classical Boltzmann equation for hard spheres. However, the process of introducing and following ternary interactions brings a lot of challenges. And I want to tell you a little bit about those challenges and what we did about them. Okay, so the first challenge is how to make sense of ternary interactions so that we can detect their contributions. Because if you remember, in the Boltzmann-Grad scaling, one actually proves that all higher order interactions, including ternary, disappear in the limit. Okay, so how do you define ternary interactions so that you can detect them? Okay, so this is what motivated us in our definition. In a typical dilute, if you have hard sphere gas, the probability of simultaneous contact, you have 3 spheres, probability of simultaneous contact of 3 hard spheres is small compared to a situation when, for example, one sphere touches the other 2. So that's one observation, which tells us that maybe we want to look at asymmetric situation first. There will be central particle that connects with the other 2. And then the other motivation comes from the work on colloids. Again, although we are not modeling colloids, I don't want to misrepresent what we do. So, but in the work of colloids, it's interesting, in this paper that I mentioned, physics paper, they said that interactions among 3 particles are determined by the sum of distances of the interacting particles, rather than on different geometric configurations. There is a very different problem in physics. It's called 3-body problem, where one looks at the various configurations and so on. We are not doing that. We want to mimic 3-particle interactions by basing it on the sum of the distances between particles. So based on 1 and 2, motivated by 1 and 2, we give the following definition. So here in the definition, we are introducing 3-particle interactions, but before that, I want to introduce ternary distance. So we're introducing ternary distance between x1 and x2 and x3. So the square of the distance is sum of the square of the distance, sum of the square of the distances between x1 and x2 and x1 and x3. So therefore asymmetric, because x1 here is central. So having defined ternary distance, we define ternary interaction. In order to define ternary interaction, we need to have a concept of this distance and the zone, okay? And zone will be introduced by this epsilon. So let epsilon be positive and consider 3 particles, I, J, K, and let us denote their positions and velocities by these 3 pairs, xi, vi, xj, vj, xk, vk, and then all in R2D. We say that particles I, J, K are in this ternary interaction with I and JK interaction if this square of the distance defined in 2.5 is 2 epsilon squared. Okay, so we call this parameter epsilon interaction zone. So let's see, if we define this thing like that, what can we do with it? So what we would like to say now is next step in modeling is if we define ternary interaction like that, what happens with velocities of these 3 particles upon interaction? Okay, so this is the first thing. We really need to go from scratch and build everything. Okay, so it's very actually simple to get a formula for the velocities for the transformation. So let me lead us through that. So consider ijk ternary interaction. So here is the square of the ternary distance is 2 epsilon squared. Let us denote by stars Vi star, Vj star, Vk star, the velocities of the 3 interacting particles after the interaction. And let's assume we are talking about elastic interaction. So we have a conservation of momentum, so that's 2.8, and conservation of energy, so that's 2.9. Okay, so now let's revisit 2.7. We are going to introduce the rescaled vectors omega-1 and omega-2, and we are going to call them impact directions of the interaction. So omega-1 is this difference, so basically the difference that appears here, xi at time t minus xj at time t minus xi at time t divided by square root of 2 epsilon, and in a similar way, omega-2 is the difference between xk and xi rescaled. So the reason why we introduced them, because 2.7 then can be rewritten as absolute value of omega-1 squared plus absolute value of omega-2 squared is equal to 1. So really the pair omega-1, omega-2 is on S to the minus 1. So it's in a higher dimensional sphere. Okay, so having that, we want to find unique. So what's the goal of this? The goal is to find formula for stars and show that there is transformation that does that for us, that's well defined. Okay, measure preserving and so on. So in order to get unique solution of the system, we impose an extra condition. Since particle I interacts with a pair of particles jk, we assume that Vj star and Vk star are transformed in the following way. They obtain from Vj and Vk by doing subtraction of C and then omega, the vector that records impact directions. This is general. If you wonder what are we doing there, if you were to think about binary, this is actually generalization of the assumption that's used in the binary case. So once we add this condition, there is unique solution, and that algebraically characterizes conservation of momentum and energy, and it gives us formula for the stars. I'm not writing them here, but there is that transformation. And we are going to now say when there is interaction, so the velocities are exchanged like that. Okay. So now what do we do once we know the change of velocities? We define the phase space of n particle system of epsilon interaction zones. So that is the set of all Zn's which record positions and velocities in R to the n, such that the ternary distance of xi, xj, xk is greater than or equal than 2 epsilon squared. Everything outside, it has a boundary. So this is the phase space, and we are assuming that ijk, in order to track things, we can get rid of this assumption later, as I will tell you by doing permutations. But for now, we will assume that ijk belongs to set in, where this is set of indexes ijk such that I is smaller than j smaller than k. This is just for technical reasons. One can get rid of that later. So the point here is you introduce the phase space, and here vector xn denotes all positions and vector vn denotes all velocities. Okay, so now you have evolution of the system of n particles. So all this, we are not there, we are not even yet, if you compare with the quantum picture, we are not yet at the position of having the Hamiltonian and linear Schrodinger equation. We are not even at the analog of that. So we need to get to Liouville equation to be at the analog of that. So particles are assumed. How do you define the motion? What's happening with them? How do you describe the motion? The particles are assumed to perform rectilinear motion as long as there is no interaction. So xi dot is vi, vi dot is 0. Now assume that at time t, the initial configuration Zn has evolved, reaching Zn of t. And assume there is an ijk interaction at time t. Then we impose that velocities at time t are going to be transformed according to 2.4t. So in other words, you have linear motion, rectilinear motion, unless they interact. When they interact, velocities change like that. So now you have definition, you have a system of n particles and you define their motion. The next challenge is, it's not obvious that what I said on the previous page, basically this 1 and 2 produce a well-defined dynamics. since the evolution is not smooth in time and the system can run into pathological configurations. So if you wonder what happened in the binary situation, this was actually, I think, PhD thesis of Alexander in 75, who established global well-defined dynamics. We couldn't use it because he considered binary interactions. However, motivated by his thesis, we were able to, his work guided us on how to obtain global in time measure preserving flow in our situation. And we did that, and the main observation that allowed us to do the work is that if a triplet of particles was in the interaction, then as the system evolves in time, local in time is easy to get. The question is how do you go from local to global? So this observation here in boldface was crucial for us. If a triplet was in interaction, then as time evolves, subsequent interaction cannot involve the same triplet of particles, the very same, okay? So thanks to that, then you have global well-defined dynamics, so you have a Liouville equation. And here is 2.15, we are writing Liouville equation. So that's transport for this n particle system is 0 when t and zn, t is from 0 to infinity, and zn, the initial configurations are in the interior of the phase space. Okay. On the other hand, when they're on the boundary of the phase space, where the d squared is equal to epsilon squared, then you prescribe that f at zn is the same as f at zn star. Well, zn star has vn star such that only the three velocities that are affected by the interaction have stars. Okay. And then also you have initial data. So the point here, 2.5 is Liouville equation in this case. And notice that we mimic this in a way such that you have a transport equation in the interior and we mimic interaction on the boundary of the phase space. If you are thinking of making analogy with quantum picture, this is like what is n-body Schrodinger in the quantum picture. This is Liouville equation here. Okay, so then one can do what one typically does with Liouville equation, derive a linear finite hierarchy of equations referred as BBGK1's Y equations. So one introduces marginal densities and one obtains BBGKY hierarchy. I will spare us formulas here because I want to illustrate something else. And by considering the number of particles going to infinity, you need to change the scaling here due to the nature of the problem. And this is different scaling, n epsilon to the d minus 1/2. And I will talk about scaling a little bit more when I compare it with Boltzmann grad scaling. So in this different scaling, what you observe in the limit, at least formally, and then you need to do the proof, you obtain ternary Boltzmann equation. So in the limit, more precisely, you get infinite hierarchy of equations, which admits factorized solution if the factor solves the new equation, that's 2.17, which has the Q3 term on the right-hand side. What the Q3 is you have now three interactions, F star, F1 star, F2 star, minus F, F1, F2, and then you have a kernel that exploits both impact directions, omega 1 and omega 2. Okay, so of course now this needs to be proved, and this is really where all the work is. The work consisted in modeling first and then getting convergence. So proving convergence is the hardest part, and what that means is identifying good configurations. Good configuration is such that when you do backward in time and evolution, you do not run into any kind of interaction. So for that, we had to redo this completely compared to binary, and we needed to produce some completely new geometric estimates. They were related, we call them spherical estimates, intersections of certain spheres with cylinders. Then we needed to introduce a transition map, which allows us to control post-collisional configurations using new ellipsoidal estimates. And ellipsoidal estimates are intersections between 2d minus 1 ellipsoids. This is related to the nature of omega 1 and omega 2 with certain cylinders. I'll not go into this here. What I want to tell you, I owe you a little bit when I said, if you remember, I said that we assumed that there is an ordering of IJK. So I want to tell you that what I described produces asymmetric version of ternary Boltzmann equation. And we were okay with that. But then by analyzing it, we realized it would be really nice if one thinks about it as a toy model that generalizes Boltzmann, it better have statistical mechanical properties of Boltzmann equation. some of those that Lauren was reviewing for us half an hour ago. Okay, and in order to do that, we realized that we needed to symmetrize the kernel. So one can indeed symmetrize and repeat the whole process. I will just mention that. So one can introduce a new phase space such that you keep track of the IJK particles that interact, and you have L, which is permutation of IJK. So in that way, you do not have to, you get rid of the assumption that I is smaller than J is smaller than K because you permute them. And what you derive is symmetrized version of the ternary Boltzmann equation. And it's not that you discover new things along the derivation of such equation. It's more like that's physically relevant with respect as if you want to think about it as generalization of the Boltzmann. Okay, so Joachim and Pavlović proved various properties of the symmetrized equation in his thesis. Okay, so now what I want to tell you from now until the end of the talk is about this recent work, which was our goal also at the beginning, to derive binary ternary Boltzmann equations. So some of you heard the version of this talk before when I talked about ternary. At that time, we didn't know how to handle binary ternary. Now we have understanding of binary ternary, which we hope can help us understand actually some of the finitely many QKs. Okay, so what are the challenges when you want to derive binary ternary? So first challenge is detecting both binary and ternary interactions. So what's the problem there? So binary interaction is described by a binary distance. Usually people call it collision. Binary distance d2 between xi and xj is epsilon. Ternary interaction, according to our language, is the square of the ternary interaction is the sum of the square of binaries between I and j, I and k, being equal to something that depends on epsilon. So now when you look at binary and ternary, first obstacle is that when you treat and track binary interactions, you are in Boltzmann-Grad scaling. So this is number of particles, and the radius and the diameter of the sphere are related by equation 2.20. On the other hand, when you track ternary interactions, you have different scaling. So this is what I like to think this in this way, which is oversimplification, but just for the purpose of understanding what's going on. It's a little bit like a lens on a microscope. So if you put lens into this scaling, of course, you see certain interactions. If you change the lens, you will see something else. Now, what do you do in order to see both? So obviously you cannot do what 220 and 221 are telling us with the same epsilon and same n, okay? However, how we resolve that is we say that we want to track hard spheres of diameter epsilon 2. So we say that all our particles are going to be hard spheres of diameter epsilon 2. We will allow them to interact using binary interactions. So that means that n epsilon 2 to the d minus 1 is like 1, but also we will allow them so that we have triplets that are interacting using interaction zone epsilon 3, such that n epsilon 3 to the d minus 1/2 is 1. So what I'm saying is there is n particles. They are all hard spheres of diameter epsilon 2. They can interact by colliding as hard spheres. And for that, the relevant scaling is Boltzmann-Grad scaling. But also you could have a group of sort of 3 that interact using ternary interactions, but then the relevant zone is epsilon 3, which turns out to be much bigger than epsilon 2, even from here. Okay? So that's first problem solved, incompatibility of scaling. Now, next problem, which is opposite in some sense. So decouple binary. So once you allow both binary and ternary, you would like to understand in the derivation process, who is responsible for the creation of the Q2 operator and who is responsible for the creation of the Q3 operator. So our framework a priori allows this picture that we have here, that you have a particle I and J, they are hard spheres of diameter epsilon 2, and they interact using binary interaction. So here their distance d2 is equal to epsilon 2. And it allows the situation that there is a particle, let's call it K, such that that particle is in, when I look at I, J, I, K ternary interaction, they are in the interaction zone epsilon 3. What I'm trying to say, our scenario allows at the same time simultaneously binary and ternary interaction. So this is bad for the proof. Many of you have been working yourself on derivation of Boltzmann related equations, and you can understand the difficulties that I'm referring to. But also it's bad if you just think about this intuitively. If you have a creature like this, then it's hard to say, is this creature going to go into Q2 in the limit, or is it going to contribute to Q3, and how are we going to decide what's the final product out of this thing? So the good news is that there are these decoupled interactions, and that's what we prove along the way. We show that as long as epsilon, so both epsilons are positive and smaller than 1, and epsilon 2 is smaller than epsilon 3, we prove that only the following two interaction scenarios are possible with non-trivial probability, and this is proved inside the proof of the convergence. So there's concept of pure binary interaction, meaning two particles here, I and J, interact as hard spheres, while all other particles are not involved in any binary or ternary interactions at the same time. So this lambda 2 is bigger than epsilon 2, okay? And bigger than epsilon 3, no binary, no ternary. Or you have a situation of a pure ternary where you have I, J, and K interacting as ternary, but you have that the distance lambda 1 is bigger than the diameter of the hard sphere, and lambda 2 is bigger than the diameter of hard sphere. So there is a ternary, but none of the particles is involved in binary. So this is like, if I were to hand wave the proof, this is what we prove at the end. And therefore, this guy will be responsible for creation of Q2, while this object will be responsible for the Q3 in the end. But of course, this is very easy to this is what's hand wavy and very, very hand wavy. So rigorously, we need to prove that. And the hardest part is challenge 3, which is stability of a good configuration. So let me describe what's new here. So assume that you have a good figuration, meaning when you run backwards in time evolution, it doesn't run into any kind of interaction. So assume that you have m particles, so 1, 2, up to m, and assume that you add sigma particles to it. So when you add, you can add 1 or 2 because they can collide as binary or ternary. So here on the picture, we are assuming that we had m particles and we are adding 2, they are called m plus 1 and m plus 2. And assume that among the m that were present, ith1 interacts with m plus 1 and m plus 2. So you have a ternary interaction. So now then you want to show stability of this interaction and you go backwards in time. So when we did just ternary, so when we had objects like this, they were excluding objects that looked like that, like ternary. Now, when we have a ternary, we need to exclude ternary, which we know how to do thanks to ternary work. But also we need to exclude possibility of a binary interaction. Also the same story, if you have binary, you have to exclude ternary and binary. So binary, ternary were handled in corresponding works, prior works, but the mixed ones are complicated. And the one that I draw on this picture is more complicated one, okay? So, and this is actually, this picture was the cause for introducing various new tools in order to do that. So there's in the paper, there's an entire section on just trying to do producing new geometric estimates in algebraic, because there's certain polynomial is relevant, discriminant of that polynomial, and so on, in order to handle this. So I'll not go into details, but we had to do a bunch of new stuff in order to handle that. And we are very happy that with Joachim that we noticed that what we had to create in order to do that might be actually quite close to what we need in order to handle the sum of QKs up to M. Okay, so I think I will finish. I'm very close to the to 6:30 at least in the European time zone. So let me tell you what we are doing now, or what we have just finished, or what our friends are doing on this topic. So with Joachim Ampezoglu, Irene Gamba, and Maja Taskovic, we studied binary ternary equation because, of course, you derive it, but then you want to see why is it relevant. So we proved small data global well-posedness involving both binary and ternary interaction for the equation involving binary and ternary interactions. This is similar to Kaniel-Shimbrot type argument. So we modified Kaniel-Shimbrot for this equation. So we get global solution for small data. Then I want to mention the work that Joachim and Pavlović and Maja Tasković are pursuing. It's in progress right now. And I want to mention it because I was very surprised to learn about one aspect of this work. So they are studying moments for the binary and ternary Boltzmann equation. And they are noticing that, so you could think for the creation and generation of, actually this is related, I think, to the creation, not propagation, but creation of moments. And Maja, I think, was on the call, so she can tell more. So my understanding is that they noticed that moments behave better for binary ternary equation than for binary alone or for ternary alone. So this is actually a feature that we could have only hoped for at the time when we were just in the dark trying to hook up ternary and interactions. So that's an interesting involvement here. Then with Joachim, we want to pursue this goal that I said at the beginning. We want to get a sum k going from 2 to m of qk's. And we think we have understanding of what's going on, but we need to find time, and beyond, we don't have understanding how to create time. And then derivation of kinetic system for mixture of gases. So this is joint work with Joachim and Pavlović and my current student, Joe Miller, where we look at the mixture of gases and derivation of the system of Boltzmann equation relevant for the mixtures. So this work with on binary ternary equations, especially convergence, allowed us to obtain certain estimates that are useful in this work on the derivation of the mixtures. So that's why I'm mentioning that. So I think that's all that I would like to say now. Thank you for your attention.
All right, so thank you very much for your very interesting talk at the crossroad between quantum and classical worlds. So is there any question? So actually, I have two questions. So the first one is about the time scale. I mean, the existence time for the Laurent theorem for binary ternary. So I was wondering if the time existence is getting worse for 2 and 3 interactions, and if it is even worse and worse and worse if you consider m interactions.
So so we are not doing anything new with respect to time. So what's happening in that respect? So it's not, if you're not, what I mentioned that the equation is better when you look at the moment. I cannot say that I have similar news in terms of the time of the existence, because time of the existence for ternary, for example, we did simple ask in the derivation. We are doing this in the L infinity spaces which are weighted with Maxwellian, and am I right? And then for ternary interaction, you have a time scale that corresponds to look at the nonlinear problem, look at the 3 interactions, and you get a typical local in time result. And then we cook up spaces at the level of the infinite hierarchy and finite hierarchy. But our goal was not, I hear your question, our goal was not to improve the time of existence. Rather, we wanted to get anything at the moment, something. Yeah.
Okay, but so is it possible to have an obstruction when m is going, I mean, when m is very large? Because if I get correctly the point, finally the goal is to have m which goes to plus infinity, right?
Yes, yes.
So is it possible to imagine that the time of existence, which should be then the infimum between all the times that are given for m interactions, is it possible for this time to go to 0?
I do not know. So for now, I know what's happening with binary and ternary. We were thinking of finite, maybe playing with infinite, but I do not know. That's an interesting question. I do not know. Yeah.
Okay, thank you. Is there any question online? Yes.
So thank you, Natasha, for the talk. So I have a bit. So my question is the following. I hope I can formulate it in a clear way. So you have this way of defining just think of the ternary, only the ternary one. So the first part of the classical that you presented. Is a, say, asymmetric situation.
I think go back to that.
You still have, say, art sphere, etc. But can you think of using some of the techniques that you developed in this context to model a Boltzmann equation? So just binary interactions in which the potential is asymmetric?
So so that's a good, thank you, Chiara, for that question. So we are thinking, we did it, it's a really good question. So we did it via doing, because we eventually we're thinking of doing binary ternary, and for binary, we are thinking of hard spheres. So we were thinking in that way, but you're right. It's conceivable to think that one can model ternary interactions via potential. And then you put ternary potential, and that would be in some sense analogous to the way how we did it in the quantum case, where there was a 3-particle potential. With Joachim, we were thinking about that. Again, time is an issue. We don't have time to do that, but we anticipate that that would be, that's conceivable. And we anticipated actually tools that we figured out in order to how to do the case with this artificial 3-particle interaction would be useful to handle the potential. So in the most recent version of, I don't think we put it online, but in the most recent version of the ternary paper, we actually even saying what the potential is, and we are writing it explicitly. So I think that's very conceivable.
Okay, then, but this is still at the ternary level. Now, if I got right your question, then my question is, I want to derive a binary, so the Boltzmann equation, the standard one. I want to replace the Boltzmann collision kernel with something that comes from a microscopic asymmetric, so non-radially symmetric interaction. To say, to really think of the initial program of Boltzmann that wanted to model molecules, and so therefore I mean, the radially symmetric was the only thing that has been done because it's just way simpler, but in principle, you might think of having a potential that is non-radially symmetric.
I hear you. I hear you. So one way, if we were thinking, if we want to talk about generalization of the Boltzmann, so one way would be, as you are saying, you look at the regular hard sphere interactions, you look at the regular Boltzmann with Q2, and then you model 3-particle interactions by putting a potential, a rescale potential that describes 3-particle interactions. So there, when you are playing with the potential, you have an option of doing it in a symmetrized way or in asymmetric way. So the way why we did it when we did just ternary, we did asymmetric. That's simpler to track. You assume that you have this combinatorial thing of I smaller than j smaller than k if I, j, k are interacting, and then you can just track them. But the problem with asymmetric one is if you study it at the level of the nonlinear PDE, it does not have the same properties as the Boltzmann equation. So we, for example, in order to have nice weak formulation and then entropy that along the lines of what Lorraine was saying, integral of Q, K, ln, F, in order to have something like that, we needed symmetrized version. So you are right. So we haven't done potential business at all, and there are 2 possibilities: one with the symmetrized and one with the non-symmetric. It's speculation at this point because we haven't done it.
Thank you very much. Thank you.
Is there a last question? So perhaps I have a last one. So if I'm correct, in the, let's say, functional setting originally from Lanford, and the one that we can also find in the Gallagher-Saint-Raymond-Texier, the Boltzmann and the solution of the Boltzmann equation is continuous, right?
Sorry, I didn't hear the last part.
Yes, so the functional setting is that we show the convergence towards a continuous solution of the Boltzmann equation, right?
Yes, yes.
And so my question is the following. Since you introduced a transport for the generalized hard spheres somehow, which is singular in the sense that it is defined only almost everywhere, how could you address the problem of the functional setting for the BGQY hierarchy? Is it something that you address in the strong sense or in the weak sense?
It's addressed in the same way. We were able to it can be reviewed and done in the same way as in the Gallagher.
Okay. Gallagher,
Saint-Raymond, and Texier.
Okay,
in
so
the revision, they have a revised version of the manuscript, so it can be done. It can be done, for example, in that way.
Okay. Okay. Thank you very much.
Yeah.
Thank you very much for your very nice talk. So I think we can thank Natasha again